Okay, so quadratic forms, section 7.2. What are those? Okay, let's look at the introduction. So until now, our focus in the textbook has been on linear equations, and in this section we're going to focus on what are called quadratic forms. Okay, so quadratic forms, I'm looking at the third line now. Quadratic forms occur frequently in applications of linear algebra to engineering. Okay, they also, and for instance, in engineering, in design criteria and optimization, I took a whole course on optimization that used quadratic forms, and then also signal processing. They can also arise in physics as potential and kinetic energy, differential geometry, economics, utility functions. We'll look at one of those, I think, on Wednesday. And then in statistics, in confidence ellipsoids, very important. So some of the mathematical background for these type of applications flows easily from the work on symmetric matrices. So recall we learned about symmetric matrices last week, in last Wednesday, and we learned that a symmetric matrix could be orthogonally diagonalized, which means that you could write the symmetric matrix as a factorization P times D. D is a diagonal matrix of eigenvalues. So A equals P times D times P transpose. So D is the diagonal matrix of eigenvalues, and then the matrix P would be a orthogonal matrix that has orthonormal columns in it. Very important idea, and we're actually going to make use of that here. So, okay. Let me see here, one moment. So what is a quadratic form? Okay, well, a quadratic form is a function. It's a function, Q, defined on n-dimensional space whose value at a vector x can be computed by the expression x transpose times A times x. A is an n by n matrix. It's a symmetric matrix. We're restricting ourselves to symmetric matrices here. And the matrix A is called the matrix of the quadratic form. So now, hold on here. The simplest example of a quadratic form would be if you took x transpose times the identity matrix times x. That will actually equal x transpose times x, which is the same as the norm of the vector x squared. All right, so that's just an example of a quadratic form. So in example 1, the book has some really nice examples. In example 1 here, they want you to compute, hold on here, one moment. Yeah, they want you to compute the quadratic form for two matrices. Okay, the matrix given in A and the matrix given in B. And what do you notice about both of those matrices in A and B? What type of matrices are those? What kind of matrices are those? What's symmetric? That's right. Good, Catherine. Those are symmetric matrices. Okay, so quadratic forms, we are restricting ourselves to symmetric matrices. Okay, well then, okay, x transpose A times x, okay, would be, I have it highlighted here. So naturally, you're going to take the matrix A times that vector x, and when you do that, that'll be first, right? When you do that, you're going to get 4x, the vector 4x1 and the vector with components 4x1 and 3x2. And then if you take then the x1, x2, that's the vector x transpose, and multiply it by the vector 4x1, 3x2, you will get then 4x1 squared plus 3x2 squared. Okay, and notice that the 4 and the 3 along that diagonal matrix A form the coefficients of x1 squared and x2 squared. Okay, are there any questions on that? All right, well, let's continue on. Let's continue on. So for B, we have the symmetric matrix 3, -2, -2, 7. And they go ahead and compute the quadratic form. Hold on here. Yeah, they compute the quadratic form for that. So the matrix A times the vector x gives you the vector that with components 3x1 minus 2x2 and -2x1 plus 7x2. Okay, and when you multiply that vector by the, that's a 2 by 1 vector, you multiply it by the 1 by 2 vector, x1, x2, you just work out the math, you're going to get in the end 3x1 squared minus 4x1 x2 plus 7x2 squared. Now notice the coefficients in front of x1 squared and x2 squared are just the diagonal entries of the matrix A, the 3 and the 7. And the -4 times that cross product term, x1, x2, that's due to the -2 entries off the diagonal in the matrix A. Okay, so the matrix A here, one moment. Okay, the matrix A has these two off diagonal terms, -2 and -2. They add up to -4. And notice that -4 is the entry in front of the we call it the cross product term, x1, x2. Okay, that's the cross product term. Are there any questions so far? Okay, well, let's just proceed on. Let's just proceed on then. So, and they also note here that if you look at these, in A and B, if you notice these quadratic forms, these quadratic forms, for part A of example 1, the matrix A had no, well, the off diagonal entries were both 0, and for part A there, the quadratic form was 4x1 squared plus 3x2 squared. So there was no cross product term. There was no x1, x2 term in that quadratic form. But on part B, when you had non-zero entries off the diagonal, you had those -2s off the diagonal, you got a cross product term. Okay, so it's just an observation. That being said, let's continue on here. So here in example 2, okay, let me just take some of this off here. Okay, in example 2, now we're having a vector in R cubed, and they're giving you the quadratic form. They're giving you the result, what Q of X is. And they want you to write the quadratic form as X transpose times A times X. So now, I think it's sort of obvious the vector X is going to have three components, X1, X2, and X3. But what would the matrix A be? What would the matrix A be? Well, what would the dimensions be? For example, 2, the matrix A, how many rows, how many columns would matrix A have? That's right, Benjamin. It'd be a 3 by 3 matrix. The matrix A would be a 3 by 3. And what entries would be along the diagonal of the matrix A? Good. 5, 3, and 2, because 5 is in front of x1 squared, 3 is in front of x2 squared, and 2 is in front of x sub 3 squared. Okay, so those are non-cross product terms, and the diagonal entries of the matrix A go with the values in front of those non-cross product terms. Okay, but now, all right, we have how many cross product terms do we have here in this Q of X, in this quadratic form? How many cross product terms do there have to be? So again, a cross product term is a term that has like x1, x2, or x2, x3, or x1, x3. How many cross product terms would have to be present in this quadratic form, for example, 2? Well, how many cross product terms do you see? For Q of X? Eleni, you see 2, but I think we know there are 3, and that's right, Abby. What's the missing cross product term here? Though it isn't really missing, but what cross product term don't you see? That's right, Eleni, x1, x3. Well, what number is in front of x1, x3? Very good. Good discussion here, good participation. What number is in front of x1, x3? That's right, Eleni, is 0. Okay, all right. So, well, all right, if we go down here then to the solution, whoops, here's the solution. Okay, here's the solution. Here's the matrix A. Okay, and you see there, now like you see the negative halves there across the diagonal, the negative halves. Why are they there? Why do you have negative halves there across the diagonal in that spot, in those spots? So the negative 1/2 is in the first row, second column. And there's another negative 1/2 in the second row, first column. Okay, first row, second column. Think of variables, the variables. First row, second column. That would have to go with what cross product term? First row, second column. That's right, Eleni. The cross product term x1, x2. Very good. So x1, x2, what's the, in example 2, what's the coefficient in front of the x1, x2 cross product term in that quadratic form? What coefficient is in front of x1, x2? So I'm looking here. What's the coefficient in front of that? -1. That's right, Hung. Well, now -1, if you divide it in half, you're going to get -1/2, -1/2. And that's why that. So in other words, what I'm trying to say, let me be a little more. Hold on here, one moment. I like to make use of the highlighter to show things here. So here's -1/2, here's -1/2, and there's the -1 in front of x1, x2. -1 divided by 2 is -1/2, -1/2. Okay, let's look here. Let's focus our attention now at the two 4s, those entries in the matrix A. The 4 is in what row and what column? The 4. Well, there are two of them, but focus on the one, the first one. Focus on. Let me see. Hold on. Focus on that one. That 4 is in what row and what column of the matrix A? Hold on. Let's get rid of this. There. All right, that 4. Okay, 3 by 3 matrix. The 4 is in what row? First, second, or third row? That highlighted 4. I know you know the answer. Come on. What row is that 4 in? That highlighted 4 there in the matrix A. That's right, Catherine. That's right, Eleanor. Second row. Okay, what column is that 4 in the matrix A? What column is that? The third. Good, Abby. Good, Catherine. So think about then the cross product term that goes with x2, x3. The cross product term that goes with x2, x3, well, that coefficient is an 8. So if you split the 8 evenly, you get a 4 and a 4. And that's where we place the 4s, in those positions. Okay, does that make, so basically well, yeah. Are there any questions on that? Who's feeling reasonably comfortable? Want to make sure before we move on. Okay, excellent, Abby. Excellent. Are there any questions? Okay. Okay, let's move on then. Let's move on. So, of course, in example 3, what they do is they give a quadratic form, okay, and they want you to compute the value of the quadratic form for different vectors. And that's just putting in, like for the quadratic form when x equals -3, and or when the quadratic form when x1 equals -3 and x2 equals 1, you just substitute in the -3 for x1 and the 1 for x2 and compute your quadratic form. You can do the same for the quadratic form evaluated at 2, -2, and the quadratic form evaluated at 1, -3. Okay, I think that hopefully that's pretty straightforward. Are there any questions on example 3, what they're doing there? All right. Well, they make a note here. They make a note that in some cases, okay, I'll highlight this too. Yeah, in some cases, quadratic forms are easier to use when they have no cross-product terms. That is, when a matrix of a quadratic form is a diagonal matrix. Fortunately, the cross-product term can be eliminated by making a suitable change of variable. So this is a little bit like calculus too. You know, when you had an integral and you had to make a substitute, and you couldn't integrate that integral, and you made a substitution, and the substitution made it then, you know, easier or possible to find the antiderivative. It's the same kind of thing here. Doing a change of variable can help make the quadratic form easier. Okay, so, all right. You've seen this before. You've seen this before. If you make a change of variable, if, for instance, if x represents a variable in n-dimensional space, then a change of variable would be x would equal p times y, or y would equal p inverse times x. Okay, and then the vector y, it's absolutely so beautiful, this. The vector y is the coordinate vector of x relative to the basis of Rn determined by the columns of P. Okay, so let me just see here. Yeah, that's right. That's right. The vector y. So looking at the left, really focusing on the left there, in that, let me remove this. So if the, hold on, if the vector x is equal to a matrix P times a vector y, the matrix product P times y can be thought of as a linear combination of the column vectors of P whose weights or coefficients are the entries of y. And that's why y is the coordinate vector of x relative to the basis of Rn determined by the columns of P. Okay, let me just, one moment here. Let me, one moment. Yeah, yeah, absolutely right. So, let me just try to I mean, I know what I want to do here. I know what I want to do, but I'll give you like a very easy example of this. So like, for instance, if you had the vector 2, 1, okay, let's say that's your vector x. Well, that can be written as 1, 0, 0, 1, okay, times, well, this is sort of, this isn't actually probably the, well, I'm just thinking here. Yeah, it's fine, it's fine. Okay, you can think of that as this matrix P times this vector y. Now, it turns out the vector y is the same as x, but the matrix product on the right can be written as 2 times 1, 0 plus 1 times 0, 1. Okay, and so the coordinate vector of x relative to the basis b, okay, where b consists of this basis here consisting of vectors 0, 1, and 1, 0, okay, that just equals 2, 1. So that's just kind of a simple example, but I wanted to just sort of, you know, give you an example of what they're talking about here. Okay, this is the standard basis, of course. You know, the vectors 1, 0, and 0, 1. It's a standard basis. But I always like to, when I see things in the, you know, when I see things in the book, let me go back to the book now. I like to kind of, I like to think of little examples to help me feel centered, so to speak. Okay, so indeed, the vector y is the coordinate vector of x relative to the basis determined by the columns of P. And there are a little example to kind of help you feel it, help you intuitively feel it. Now, what's this change of variable that we're going to be doing here? What's this? Well, the change of variable is x equals P times y. If we do that, okay, well, what's going to happen to the quadratic form? X transpose times AX is equal to PY transpose times A times PY. But the product of the transpose of a product is the product of the transposes in reverse order. So let me just sort of take a little bit of stuff off here. Okay, so that means PY transpose is Y transpose times P transpose. Okay, and then PY is just PY. And we can factor this matrix product appropriately this way, because matrix factorization is associative. I can write the quadratic form X transpose AX as Y transpose times P transpose AP times Y. Okay, I can do that. Now, what is P transpose times AP equal to? Okay, what is P transpose times AP equal to? Well, remember, and I'm just making a note here, we're assuming that matrix A is symmetric, right? So remember from section 7.1, if A is symmetric, okay, and let me see, I got my stylus here too. If A is symmetric, then A is going to equal P times D, diagonal, times P transpose. Okay, if A is symmetric. In other words, we can find a matrix P that we can find an orthogonal matrix P. You know, P is orthogonal. And if P is orthogonal, this means that P transpose is equal to P inverse, right? That's the beauty of an orthogonal matrix. So this matrix P consists of the eigenvectors of the matrix A, but we ensure that we have a that the eigenvectors of P are all orthogonal. Okay, so if A equals P times D and of unit length. So if A equals P times D times P transpose, well, okay, that's fine. That's fine. But then what would P transpose times AP equal? Well, what we can do here is we can multiply on the left side of that matrix equation, we can multiply by P transpose. We can do that. What's P transpose times P equal to? What would this equal here? Man, hold on. It equals the identity. Good, Haley, good. Got a little bit too much writing here. Good, Eleanor, absolutely right. This is going to be the identity because P is an orthogonal matrix. So now you have P8 transpose times A equals D times P transpose. Okay, but what we can do now is, you know, I just want to kind of keep things separate here. I have P transpose times A now. So I'm just keeping things a little bit separated here. I have P transpose times A, and I can multiply on the right side by the matrix P. So I would have then on the right side, I'd have the matrix D times P transpose times P. So all I did was I took this equation here and I multiplied on the right side of that equation, both sides of that matrix equation, by P transpose. Well, P transpose times AP is going to equal what? Well, what's P transpose times P equal to, everybody? What's P transpose times P going to equal? That's right, Eleanor, the identity. And therefore, P transpose times AP, P transpose times AP will equal a diagonal matrix. It will equal diagonal matrix. Okay, are there any questions on that? This is the beauty of an orthogonal matrix. They're so easy to work with. They take time to get, but once you get them, the world kind of opens up for you, you know. And I'm going to show you an example of this as well. Are there any questions before I go back to the book? Okay. All right. Well, now that we've established that P transpose times A times P equals the diagonal matrix, We've established that. Now when we're back in the book here, now we've justified that. And so they say that P transpose times A times P is a diagonal matrix. We just showed that. And so the quadratic form becomes, with this change of variable, the quadratic form becomes y transpose times d times y. And see, there won't be any all the entries of the quadratic form are going to be there won't be any cross product terms. That's what you're doing here. You eliminate cross product terms. So I want to go right to an example. The book has a nice example, and example 4. But I'm going, and that's nice, but I'm going to do a little example of my own here. But it'll still relate to an example in the book. And actually, what I'm going to do is example 5 here from the book. Okay, so let's go ahead. Are there any questions before we move forward here? Who's feeling reasonably comfortable? Okay, good, Eleanor, good, Olivia. Excellent, excellent. Okay, well, let's see here. So let's go into our files here. And here's an example that I'd like you to copy down. And we're going to do this example. Okay, so let me give you a moment to copy this example down. Section 7.2. Okay, all right. So, well, this is certainly an interesting ellipse here. Okay, so like you're used to like for instance, if you have like let's say you had x squared over 1 plus y squared over 4 equals 1. Let me do a little. Now notice in this, I'm trying to. How many recall seeing ellipses, studying ellipses in high school? Maybe in algebra 2. Okay, Eleanor recalls it. I think pretty much most of you would have seen it at some point. So you know, this here, this ellipse. That's not very pretty. Sorry, I think I can do a little better than that. But let's just kind of hold on here. Let me maybe use black here. Hold on. Man. Okay. So we have X, we have Y, and maybe I can get rid of this here. Hold on. Sometimes the mouse is, like for erasing, the mouse is usually better. So I've drawn an X and a Y axis. And if I draw the ellipse here, okay, not perfect, but it's centered at the origin. And what's the x-intercept going to be based on this equation for the ellipse? This ellipse is in standard form. Of course, we focus on the 1, right, to determine the x-intercepts. So what would the x-intercepts be? Here and here. X-intercepts, you set y equal to 0, right? You set y equal to 0. If y equals 0, that's right. Good, Benjamin. The x-intercepts are -1 and 1. The y-intercepts, okay, are when you set the x equal to 0. So what would the y-intercepts be for this ellipse? This is an ellipse, right? What would the y-intercepts be? What would this value be and this value be? So of course you focus on the 4 there. Set x equal to 0, solve for y. You're almost right, Eleanor. There we go. You got it right. The second chat there. That's right. 2 and -2. Okay. So how many recall doing this? You know, when the ellipse is in standard form, you look at the denominators and take the square root of the denominators, and that gets you your intercepts. You know, plus or minus 1, comma 0, and 0, comma plus or minus 2. How many remember doing that in high school for finding intercepts of an ellipse in standard form? Okay, Eleanor, and maybe getting a little bored with it. Eleanor recalls it, Olivia recalls it. Sure. And you know, those are nice ellipses, but you notice those ellipses don't have any cross product terms. So, I mean, what I'm trying to say is an ellipse in standard form, like this ellipse, and we you know, that we can identify the intercepts easily and graph that ellipse, no problem. Okay, so an ellipse that goes up and down or like sideways, those are perfect. But this kind of ellipse here has a cross product term. So this kind of ellipse is going to be what's called an oblique ellipse. How many heard of oblique ellipses? Maybe in high school. That's right. And Eleanor recalls them. And as you might also recall, they're very difficult to graph, right? If I recall in high school, when I learned about oblique ellipses, I had to like plot, maybe like I had to plot a lot of points on the ellipse to figure out what it looked like for an oblique ellipse. How many kind of maybe had to do that? You just plotted a bunch of points, maybe 20 points, and then did anybody have to do that? Maybe you didn't, but all right. Well, at any rate, we agree that these oblique ellipses, like the one you have here, are they are difficult to graph. Okay, because how do you identify what the intercepts are? Okay, well the reason I'll tell you, the reason that these ellipses are difficult to graph is because the axes, okay, that sort of define the ellipse, we call them the principal axes, they're not the x and the y axis. They're different axes. So if we could identify these new principal axes, then the ellipse would be just as easy to graph as an ellipse that you learned back in high school. Okay, and so that's what we're going to do here. Are there any questions? Okay, what we want is a geometric view of the principal axes. So, okay, first thing we're going to do, what do we have to identify for this ellipse? If we look at the left-hand side, here, and the picture's getting a little cluttered, but the left-hand side here of this equation is what? 5x1 squared minus 4x1x2 plus 5x2 squared. That is what kind of form is that? The left-hand side of that equation. In other words, what I'm trying to say is this. Here's what I'm trying to say. Hold on. Well, hold on. Let me write it this way. Hold on, let me get this off here. So 5x1 squared minus 4x1 x2 plus 5x2 squared. Can that be written as a vector x times a matrix A? Well, I'm sorry, a vector x transpose times a matrix A times a vector x. Can I write the left-hand side of my ellipse equation as a quadratic form? So 5x1 squared minus 4x1 x2 plus 5x2 squared. I can tell you that can be written as a quadratic form. Can you identify what the vector x would be? Can you identify what the matrix A is going to be? What's the vector X going to consist of? What variables, class? That's right. Good, Eleanor. X1, X2. And the matrix A is a 2 by 2. What's going to go along the diagonal of the matrix A? What entries? Here and here. That's right. Good, Eleanor. 5 and 5. Okay, what entries then are going to go, because we have a 5 here and we have a 5 here. Okay, what are the entries off the diagonal going to be? Well, Eleanor, we are going to work with the -4, but what do? That's right. That's right, Eleanor. We divide it by 2, we split it in half, and so we get -2 and -2. And what we're going to do, class, is we're going to make a change of variables. We're going to make the change of variables where X equals a matrix P times a vector Y. So vector X equals a matrix P times a vector Y. We're going to make a change of variables to remove the cross products from this elliptical equation. So let's go to the solution here. Okay, first of all, the matrix A we know is 5, -2, -2, 5. We can orthogonally diagonalize that matrix A since it's a symmetric matrix. Okay. So here you're going to use MATLAB we can use MATLAB to get our eigenvalues and eigenvectors. You've done that. You've done it many times on the exam 4. There were 3 questions on part 1 where I mentioned about using MATLAB for many of the exercises, but there were 3 of them where you had to find solutions of a particle moving, where you had to work it out by hand. So you've done this many times. In MATLAB, if you put this matrix A in and use the command, that V comma D equals I of sim of A, and I don't have enough room to write it. I never, hold on. Let me do this right. Hold on. Let's do it right here. The reason we use V and D is because D holds the eigenvalues. That matrix holds the eigenvalues, and the matrix V holds the eigenvectors. Okay, so this is the command you'll use, and you'll get your eigenvalues and eigenvectors. And the eigenvectors are automatically orthogonal because they come from different eigenspaces. So remember, for a symmetric matrix, when you have different eigenvalues, the eigenvectors from those different eigenspaces are automatically orthogonal. All we have to do is normalize them, so we have length 1. Well, then we do that, and then that's our matrix P, and then our matrix D is here. So we're going to use a change of variables, X equals P times Y, where we've identified the matrix P right here. Okay. And I note here again that if A equals P times D times P transpose, then D will equal P transpose times A times P. We showed that, but I have it written here. Let me give you a moment to catch up. Please let me know if you have any questions. Okay, and when you're ready, we'll move to the next page. Just give me a thumbs up when you're ready to go to the next page, and we will go there. Okay, Eleanor's good to go. Good. Lewis is ready. Excellent. Okay, Marvelous is good. Thank you, Marvelous. Okay, so, all right. All right. So we know what our matrix P is. We know what our matrix D is. We're going to make the change of variables, X equals P times Y. Now let's get back to our ellipse. Here's the ellipse. So the ellipse is 5x1 squared minus 4x1x2 plus 5x2 squared equals 48. By making the change of variables where the vector x equals P times Y, I'm going to rewrite the left-hand side of the ellipse in a nicer form. So by letting x, the vector x equals P times the vector y, and we've identified the matrix P already. I can get this quadratic form. I can get it as y transpose times, hold on here, I can get the quadratic form written as y transpose times P times y. Okay. And of course, the vector y has components y1 and y2. And so what I'm going to get then is a new quadratic form, a new quadratic form, where I have 3y1 squared plus 7y2 squared equals 48. Absolutely amazing. And so that means then that our ellipse, in terms of the equation of the ellipse, in terms of the variables x1 and x2, is equivalent to the equation of the ellipse in terms of the new variables y1 and y2, where y1, y2, that vector, is equal to p transpose times the vector x. Now, the way I'm getting that is that if we remember here, x equals p times y, but that means that if I multiply by p transpose on the left side of the equation, when I did my change of variable here, I'll get p transpose times py, but p transpose times p is the identity. Hence, p transpose times my vector x p transpose times my vector x is equal to y. That's how I get this here. Trying to justify how we get that. Okay, and so we can think of the vector y. We can think of the. I want to say this the right way. Hold on, just a moment. We can think of x1 and x2, those variables. Hold on here. Let's say this the right way. Yeah, the x1, x2, those variables are the coordinates of the vector y relative to the basis, where the basis vectors are 1, root 2, negative 1, root 2, and 1, root 2, 1, root 2. Okay, and I'm going to show you a picture of that. But let me know when you're, are there any questions? All right. Just going to ask kind of a survey question now. How many of you find it helpful, these little, things I write with the pen on the page? Okay, Eleanor said right away. Okay, very good, very good. I have a colleague that kind of records his lectures like ahead of time, but I like doing it. I like doing it kind of live personally, because then I can add these things to the lecture, and and it just, for me, it works for me, and I hope, and I'm glad it's working for you too. Okay, so give me a thumbs up when you're done copying, and then we'll move to the next page. I'm going to show you a picture of this, what's going on here. Okay, I heard a chat here. All right, Benjamin's ready to roll. Okay. So let's remember what we're doing here. What is our goal here? What is our goal? We have an ellipse. We have an ellipse. 5x1 squared minus 4x1 x2 plus 5x2 squared equals 48. We have this ellipse, okay, that I mean, up to now, the only way you could graph that ellipse is by plotting like 100 points or something, and of course we want to try to, with our linear algebra knowledge, we don't need to graph 100 points to graph that ellipse. All we need to do is rewrite the equation of the ellipse. Okay, rewrite it using the change of variable. Rewrite it as an equation in terms of new variables y1 and y2 that are much easier to work with. Okay. Now let me ask you this. So what does this matrix down here sort of remind you of? It's a transformation matrix, right? You're taking, good. That's right, Benjamin. This is a rotation. This is a rotation here. Okay, you are rotating. You are rotating coordinates x1 and x2 to get new coordinates y1 and y2. That being said, let's go to the next page. Okay, so this is really from way back in section 1.9. You have a rotation matrix here. This P transpose is a rotation matrix. And the rotation is rotating a 45-degree clockwise rotation. Okay, so let me let you copy up to here, and then we're gonna look at this picture here, where I've graphed this ellipse. I've graphed it using linear algebra knowledge. Okay, let me give you a moment to catch up here. Okay, so this actually, there's a figure 3 in your textbook that has this exact picture on the left for this ellipse. But the rotation, so there are multiple ways of thinking about this. But perhaps one way is to think of it like this. This might be easiest for some of you. These vectors here, the transformation matrix has column vectors that consist of the transformation of the E1 vector, and then I'll put this below, the transformation, well, I'll put it above, transformation of the E2 vector. Okay, so that means, for instance, that means that, got to be a little careful here now, 1, 0 under the transformation gets mapped to 1 over root 2 and negative 1 over root 2. Okay, so the transformation matrix, the fact that the columns consist of the transform vectors of those unit vectors E1 and E2, That's back, that's a theorem that you learned back in section 1.9, theorem 10. How many does that kind of ring a bell? Theorem 10 or section 1.9. All right. Thank you, Eleanor. It's been a little while maybe, but maybe not that long. So 1, 0 gets mapped to 1 under the transformation, I'll put a T here, under the transformation. 1, 0 gets mapped to 1 over root, the vector 1 over root 2, negative 1 over root 2. And 0, 1 under the transformation would get mapped to that second vector, which would be just 1 over root 2 and 1 over root 2. Okay, one moment here. Okay, so all right, so that being said, I want to just do something here. Hold on, class. Hold on. One moment. I want to just rewrite it again here. And you have it, but I just want to rewrite it. Okay, so 1, 0 gets mapped under the transformation to 1 over root 2 and negative 1 over root 2. And then 0, 1 gets mapped under the transformation to positive 1 over root 2, positive 1 over root 2. Okay. And I just wanted to rewrite it again. My instincts were telling me to rewrite that again. And that's what I did. So let's see now how this applies in regards to the picture. Well, all right, here in the picture, I have the point 1, 0. 1, 0 gets mapped to 1 over root 2 and negative 1 over root 2. Okay, so in other words, we're taking the x1, x2 axes and we're rotating them so that we have the new y1, y2 axes. So the x1 axis got the point 1 root the point 1, 0 got rotated to the point 1 over root 2, negative 1 over root 2. And so that forms the y2 axis. The y2 axis has to pass through the origin and that point. On the other hand, the 0, 1 point under this transformation gets mapped to the point 1 over root 2, 1 over root 2. Notice that's the eigenvector, right? The normalized eigenvector. And so the x2 axis gets mapped to the y1 axis. Okay, the y1 axis has to pass through the origin and that eigenvector. Okay, so this is exactly what you have in the picture in figure 3 in your book just before example 5. So now what I do is I say, okay, well let me take my elliptical equation in terms of my new variables and let me get it in standard form. And if I get it in standard form, the intercepts are going to be the y1 intercepts are going to be 4, 0 and negative 4, 0. And that's what I've drawn here. And the y2 intercepts are going to be 0 plus or minus root 48 over 7. And root 48 over 7, square root of 48 over 7 is, hold on, that equals 2.6. Okay, so that's going to be here and here. The intercepts on the y2 axis. So you have intercepts of plus or minus 4, 0 on the y1 axis, and then you have intercepts of plus or minus square root of 48 sevenths on the y2 axis. And look at this, you were able to, now you can graph that ellipse easy with these new axes. You have new principal axes, y1 and y2, which are more convenient than the axes x1 and x2. And you can see it's a 45-degree clockwise rotation that the effect of this transformation is. Okay. So isn't this amazing? Look at all the knowledge. Look at all the knowledge in linear algebra that you have brought to bear here. I mean, basically this example combines, I don't know, maybe, I mean, I'm not sure, but at least 50% of what you've learned, don't you think? I mean, how many think this is an absolutely beautiful application for Chapter 7? The fact that orthogonal diagonalization allows you to do this. Eleanor loves it. Catherine thinks it's beautiful, very beautiful. It is. It really is. And we can do a lot of things in engineering that would normally be very complicated just by changing your frame of reference. And that's what orthogonal diagonalization allows you to do. Are there any questions on this? Who else thinks it's pretty cool? I'm very glad that Eleanor and Catherine like it, but how many, do we have a few other, maybe thumbs up? All right, Abby loves it. Good. We are where we are in the 21st century because we can do things like this. Go to the moon, maybe go to Mars, all this stuff, Okay, well, I want to just point out a few more things in the textbook here, and I think in about 10 minutes here I'll be able to let you work on that on your new homework. But May I go to the ebook? Is anybody still copying anything down, or are we good? Okay, hung's good, excellent. Hung on's good, very good. The book kind of leaves out these details here, you know, like the standard form and all that. But I think they maybe think you would figure it out, and that's fine. But hey, you're here in class, and I'm here to help you. So I like to sometimes, I mean, if I can fill in gaps to help you understand, I'm very happy to do that. Okay, okay. Then if we're good, I'll go to the ebook. If we're good with this. Okay. All right, one moment. Let me get the ebook here. I want to just get to. So this was really example 5 that we just did. Okay. That being said, quadratic forms can be classified. Okay, quadratic forms can be classified. You have here graphs of quadratic forms. Okay, so in the figure below, they have, z equals q of x. Let me just make a note here. So hold on. The quadratic form is qx equals x transpose times ax. And they're going to let z equals q of x. They're going to let z equals q of x. And that's how they plot. So the x, the vector x is, x1, x2, and then z is a function of x1 and x2. So z is a surface. Okay, and so we get these surfaces. And incidentally, in multivariable calculus, Math 280, we graph surfaces as well. I'm actually teaching multivariable calculus over the summer. If it's a night class, so it'll go the whole summer, but at least it won't be, some of the summer classes, they're very condensed, the 6 weeks, but my class will go 10 weeks. So if anybody's interested, needs to take Math 280, you'd be very welcome to sign up for my class. There's still space. But all right, that being said, so here's some quadratic forms. And you see, depending on what coefficients are in front of x1 and x2 squared, that determines what the quadratic form will look like. So like, for instance, in this picture here in figure A, you have a 3 and a 7. Now that would correspond to eigenvalues 3 and 7 for some matrix A. So when 3 and 7 are positive, you have a quadratic form. You have a quadratic form that we call positive definite in figure A. But on the other hand, in figure D, the eigenvalues -3 and -7, okay, are negative, and you have a quadratic form or parabola that opens downward. That quadratic form would be called negative definite. Okay, and then in figure C, okay, you have a quadratic form here in figure C that is that the z values are sometimes positive and sometimes negative. Well, that's called negative. The quadratic form is indefinite. You have a +3 and a -7. That's a positive eigenvalue and a negative eigenvalue. So that's called an indefinite quadratic form. And that's what they mention here in the definition here regarding positive definite, negative definite, and indefinite. Okay, now sometimes you'll have an eigenvalue that is equal to 0. And if that happens, like for instance, if you had a eigenvalue of 0 and then all the other eigenvalues are positive, we would call that positive semi-definite, the quadratic form. And if the quadratic form were such that, well, if the eigenvalues, if you had an eigenvalue of 0 and then eigenvalues that are the rest are negative, you'd have semi-definite. Okay, so this is really relates to theorem 5 here, where they talk about what would classify a quadratic form. What would classify it as being, well, positive definite, negative definite, or indefinite. Okay, and it's sometimes helpful just to see a picture. Sorry, I didn't mean to take that away right away, but I want to, you know, this is a theorem 5. I'll let you look at it. We talked about it though. Here they have pictures of positive definite, negative definite, and indefinite graphs. Okay, on the left here. So that's just you know, just sort of sums up then the section 7.2. Are there any questions on that? Okay, let me stop the recording.